Hello everyone, I am Bireshwar Roy. I am currently pursuing my third year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this course, I will be discussing some previous year GATE physics questions and try to solve them with proper explanations. This question was asked from the GATE Physics paper 2021. This is a multiple select question of 1 marks and this question was asked from the topic electromagnetic theory. The question is, a material is placed in a magnetic field intensity capital H. As a result, bound current density Jb is induced and magnetization of the material is capital M. The magnetic flux density is capital B. Choose the correct options valid at the surface of the material. Option A is divergence of M equals to 0. Option B, divergence of B equals to 0. Option C, divergence of H equals to 0. And the last option, option D, divergence of JB equals to 0. Now as this is a MSQ, so it is possible to have multiple options correct. We'll check each and every options one by one. Let us see the solution part now. Before going to the solution part, we will first recap some basics related to the magnetic material in a magnetic field. We know magnetization of a magnetic material when it is kept under an external magnetic field B, it provides us with a macroscopic description of the atomic currents in the matter. Mathematically, magnetization of a material is defined as summation over all the magnetic dipole moment of the matter divided by a volume element when volume tends to 0. Here, magnetization of the system is a macroscopic quantity, but your magnetic dipole moment is a microscopic quantity. If we want to visualize what is the magnetization of a system physically, we need to consider tiny current loops formed in the matter due to the cyclotron motion of the electrons when the material is kept under a magnetic field. Now this tiny current loop will have some magnetic dipole moment. These magnetic dipole moments will basically contribute to the magnetization of the system. Now for uniform magnetization, the volume bound current density Jb is 0, but the surface bound current density Kb is non-zero. This is because for uniform magnetization, all the tiny current loops formed inside the bulk of the system will cancel each other. Hence, you will have a 0 volume bound current density Jb. But at the surface, the cancellation will not happen. So, effectively, you will have a non-zero surface bound current density Kb. In the case of non-uniform magnetization, both the current densities Jb and Kb are non-zero. Now we'll try to relate these current densities Jb and Kb to the magnetization of the magnetized material. For this, we'll consider a magnetized material kept under an external magnetic field B and the system will have volume V. Inside this system, we'll consider elementary volume dV, whose coordinates is x dash, y dash, z dash from the origin. And we'll consider another external point P which has the coordinate x, y, z. So from the volume element, the external point P will have position vector capital R, which is basically your R vector minus R dash vector. Now we know vector potential due to single current loop having magnetic dipole moment small m is given by mu naught by 4 pi m cross r by r cube. Now for a magnetized material having magnetization capital M, the vector potential A vector is given by mu naught by 4 pi integration over M vector dV cross product with capital R vector by capital R cube. Now after some simplification with the help of vector algebra, we can show this A vector is basically summation of two terms. Now here the first term is due to the contribution from the volume of the system, that is the bulk of the system, but the second term is due to the contribution from the surface of the system. And from the first part, this curl cross M is basically your volume bound current density, and in the second term the M cross N cap, this is your surface bound current density. Hence, the volume bound current density is defined as JB equals to curl cross M vector, and surface bound current density is KB equals to M cross N cap. Now we'll see the solution of the given question. We have already seen when magnetic material is placed in a magnetic field, it will get magnetized, and it will give rise to two types of current densities, that is volume bound current densities and surface bound current densities. The volume bound current density is given by JB vector equals to curl cross M, and your surface bound current density is KB equals to M cross N cap. Now we know the magnetic flux density or magnetic field inside the material is given by mu naught times your H vector plus the magnetization vector M. Now from the Maxwell's equations, we know divergence of B vector is 0. For a magnetized material, this B vector is mu naught times H vector plus M vector. If we put that relation in the equation, then you will get mu naught times divergence of H plus divergence of M equals to 0. It will basically give divergence of H equals to minus of divergence of M. Now our system has a volume bound current density JB. This means our system has non-uniform magnetization. So the divergence of M vector for this system is non-zero, and it will give rise to divergence of H is non-zero. Now divergence of JB is divergence of curl cross M, because JB is defined as curl cross M, and this term is also 0, so your divergence of JB is 0. So if you see the four options, among the four options, this B option and the D option is correct. According to our solution, the option B and option D, those are divergence of B equals to 0 and divergence of JB equals to 0 are the correct options for this question. This question is from the GATE Physics paper 2021. There is a MCQ type question having 1 mark, and the question was asked from the topic solid state physics. The question is, choose the correct statement from the following. Option A, silicon is a direct bandgap semiconductor. Option B, conductivity of metals decreases with increasing temperature. Option C, conductivity of semiconductors decreases with increasing temperature. And the last option, option D, gallium arsenide is an indirect bandgap semiconductor. So here four options are given. We have to choose the correct statement among these. So we'll verify all the options one by one, and we'll check which option is correct among these. Let us see the solution part now. The first option, option A, is false because silicon is an indirect bandgap semiconductor. Now this is a typical EK diagram of an indirect bandgap semiconductor. The bandgap is defined as the difference between the energy at the conduction band edge and the energy at the valence band edge. Now, in order to have an electronic transition from valence band to conduction band, the electron has to gain the energy equals to band gap of this system, that is EC minus EV. But this is not only the case, because in order to have the transition, electron has to change its momentum to reach the conduction band edge. That is the momentum difference between these conduction band H point and the valence band H point. Now this extra momentum to the electron is provided by the phonon, which is basically the quanta of the lattice vibration of this semiconductor. So in the indirect semiconductor, the electron rising from valence band to conduction band will change its energy as well the momentum. The second option, option B, is true, which is conductivity of metals decreases with increasing temperature. From the root model, we know conductivity of a metal is given by N E squared tau by M, where N is the carrier number density, E is the electronic charge, tau is the relaxation time or mean collision time, and M is mass of electron. Now with change of temperature, the carrier number density N doesn't change much. Effectively, it will remain unchanged. But the collision time or relaxation time decreases with increasing temperature because the scattering probability between the electron and ion core increases. So your option B is correct. Now the option C is false because conductivity of semiconductors increases with increasing temperature. We know as the temperature increases, more and more electrons will be excited to conduction band from valence band, and it results in the number density of electrons and holes will increase in conduction band and valence band respectively. Hence, the conductivity of the semiconductor will increase as the temperature increases. Your option D is false because gallium arsenide is a direct bandgap semiconductor. If we see the EK diagram for the direct bandgap semiconductor, the edge of the conduction band and the edge of the valence band lies at the same K point. So, in order to have a transition, electronic transition from valence band to conduction band, the electron needs only the energy which is equal to the band gap of the semiconductor. Electron doesn't need any momentum change because the edge of the conduction band and the edge of the valence band lies at the same K point. So in direct band gap semiconductor, the electron rising from valence band to conduction band will only change its energy. So we checked all the statements one by one thoroughly, and we found that only the options B, that is conductivity of metals decreases with increase in temperature, is the correct one for this question. This question was asked in the GATE Physics paper 2021. This is a MCQ having 2 marks, and the question was asked from the topic electromagnetic theory. The question is, an electromagnetic wave having electric field E vector equals to 8 cos kz minus omega t along y cap direction, and the unit is volt per centimeter, is incident at 90 degree, that is normal incidence, on a square slab from vacuum with refractive index in naught equals to 1 as shown in the figure. So according to this schematic diagram, an electromagnetic wave is incident on the surface 1 of the square slab at 90 degree. The slab is composed of two defined materials with refractive indexes N1 and N2. So in the square slab, two regions, that is green and blue, are divided by this diagonal, and this green region has refractive index N2 equals to 1.1 and this blue region has refractive index 2.2. Assume that the permeability of each medium is the same. After passing through the slab for the first time, the electric field amplitude in volt per centimeter of the electromagnetic wave which emerges from the slab in region 2 is closest to, there are 4 options given. Option A 11 by 1.6, option B 11 by 3.2, option C 11 by 13.8, and the last option, option D, 11 by 25.6. So in this question, to solve this, we have to do basically we have to find the amplitude of the electric field in region 2 after getting reflected from this diagonal interface. Let us see the solution part now. According to the schematic given in our question, the electric field of the EM wave in region 1 is given by E vector equals to 8 cos kz minus omega t along y cap direction. And the EM wave is propagating along z cap direction in the region 1. Now, some portion of the incident EM wave in region 1 will be transmitted inside the slab and will fall on the diagonal interface separated by these two regions. Two situations may occur in this case. First one is the angle of incidence on this diagonal interface is less than the critical angle for total internal reflection. Then some portion of the incident EM wave will be reflected back in this region, and the remaining portion will be transmitted from this interface in this region. The second possibility is the angle of incidence is greater than the theta c, that is critical angle for total internal reflection. Then total incident wave on this interface will be reflected back in this region towards this region 2. Hence, we'll first check what is the critical angle at the diagonal interface. Now, in case of total internal reflection from an interface, if the EM wave is incident on the interface at an angle equals to the critical angle theta c, then after reflection, the EM wave will travel along this interface. So the reflection angle is 90 degree. To find this critical angle in our case, we'll use Snell's law. Now applying the Snell's law, we'll get sin theta c divided by sin 90 degree equals to n2 by n1, which is basically 1.1 by 2.2. So our theta c, the critical angle for total internal reflection, is sin inverse half, that is 30 degree. And we have seen earlier that angle of incidence at this interface is 45 degree. So in our case, the angle of incidence at diagonal interface is larger than the theta c, which is 30 degree. So for sure, the total internal reflection will take place at the interface. As total internal reflection is taking place at the diagonal interface, then the intensity of the incident EM wave on this interface I1 will be equal to the intensity of the EM wave after getting reflected from the interface, that is I2. So I1 equals to I2, and I0 is the intensity of the EM wave in region 1, which is given by half multiplied with C epsilon naught E naught square, where E naught is given in the question, that is 8 volt per centimeter. Here C is the velocity of light or EM wave in vacuum, epsilon naught is the permittivity in vacuum. Now at interface 1, we'll apply the Fresnel equation for transmittance. As the EM wave is propagating along z cap direction and electric field vector is along y cap direction, so it is the EM wave with in plane polarization. Now for in plane polarization, the transmitter's formula is this, which is T1 equals to 4 N1 N0 by N1 plus N0 whole square. Now if we put the value for N0 N1 in this formula, we'll get T1 is 55 by 64. So we get the transmittance for the interface of region 1 and this region. So the transmitted light from the region 1 to this region of the slab is given by I1 equals to T1 multiplied with I0, that is 55 by 64 into I0, which is your I2, because our I1 equals to I2 in this region because of total internal reflection. Now we will calculate the transmittance value for this interface, that is interface 2, and it is given by T2 equals to 4 N1 N0 by N1 plus N0 whole square, which is same as the T1, that is 55 by 64. Now the intensity of the EM wave in region 2, that is given by I3, is basically T2 times your I2. Now T2 is 55 by 64 and I2 we have calculated in the previous slide, that is 55 by 64 I0. So your I3 is 55 by 64 whole square multiplied with I0. Now I3 can be written as half C epsilon naught E03 whole square, while E03 is the amplitude of the electric vector in region 2 and I0 is half C epsilon naught E0 square. So if we just cancel out the half C epsilon naught from both sides, then we have E03 whole square equals to 55 by 64 whole square times E0 square. So E03 is 55 by 64 E0. Now E0 is 8 volt per centimeter as given in the question. Effectively we have E03 in region 2 is 55 by 8. So if we just divide the numerator and denominator by 5, then we will get 11 by 1.6, which is our E03 in region 2. So our option A is correct. According to our solution, after passing through the slab for the first time, the electric field amplitude in volt per centimeter of the electromagnetic wave which emerges from the slab in region 2 is closest to 11 by 1.6, that is option A is the correct answer for our question.